Welcome, focused learners, to this explainer. We're diving straight into the unseen world around us. Everything you see, touch, or feel, it's all made of something fundamentally microscopic. Today, we are going to break down exactly how the building blocks of matter actually work.
Let's kick things off with a massive thought experiment, one that actually puzzled ancient philosophers. Imagine you've got a block of material. You cut it in half. Then you take that half and you cut it in half again, and again, and again. The big question here is, do you eventually hit a wall where you literally cannot cut it anymore, or can you just keep dividing it infinitely?
To figure that out, here is our roadmap for the explainer today. We're going to hit 5 key stops: the mystery of matter, the rules of chemical combination, meet the atom, molecules and ions, and finally we'll wrap up by writing chemical formula. Let's get into it. Stop number 1, the mystery of matter. We're looking back at the earliest thinkers who tried to crack the code of the universe using nothing but their minds. You know, it's pretty fascinating that the idea of an indivisible particle started as pure philosophy centuries before science could actually prove the thing. Around 500 BC, over in India, Maharishi Kanad put forward this idea that if we keep dividing matter, we'll eventually hit the smallest possible particles, which he called parmanu. Right around the exact same time in ancient Greece, Democritus and Leucippus had the exact same realization, coining the term atoms, which literally means indivisible. But it wasn't until the end of the 18th century that scientists finally had the tools to experimentally distinguish between basic elements and more complex compounds. Which brings us perfectly to our second stop: rules of chemical combination. Let's jump to that late 18th century era when Lavoisier and Proust finally brought hard experimental proof to the table. So check out Lavoisier's famous tilted flask experiment. Imagine you have a sealed glass flask containing 2 completely separate solutions, say barium chloride and sodium sulfate. You weigh the entire setup. Then you just tilt the flask so the chemicals mix together and react. You weigh the whole shebang again, and guess what? The mass is exactly the same. There's absolutely no change. This brilliantly proved the law of conservation of mass. Basically, mass is never created or destroyed in a chemical reaction. The atoms are just rearranging themselves. And that leads right into the second major rule, the law of constant proportions, established by Joseph Proust. Think about water. Whether you scoop that water out of a river, synthesize it in a lab, or catch it from a rain cloud, if you break down exactly 9 grams of it, you will always, without fail, get exactly 1 gram of hydrogen and 8 grams of oxygen. Compounds always combine in exact, definite mass ratios, totally regardless of where they came from. Okay, so we have these laws, but how do we actually explain them? Enter British chemist John Dalton in 1808. Dalton was this poor weaver turned teacher, and he proposed a total game-changer of a theory. He argued that literally everything is made up of tiny, indestructible atoms. He said all atoms of a specific element are completely identical in mass and properties, but they're totally different from atoms of other elements. And, crucially, they combine in simple, whole numbers to form compounds. This elegant idea neatly explained both Lavoisier's and Proust's laws in one fell swoop. Now that we know they exist, it's time for part 3, meet the atom. Let's figure out what these microscopic entities actually are and how on earth we measure them. To really grasp their unimaginably small size, think about a single grain of sand. To an ant, that sand grain is a pretty huge building block, right? But an atom of hydrogen is phenomenally smaller than that grain. We're talking so incredibly tiny that millions of atoms stacked right on top of each other would barely equal the thickness of a single sheet of paper. Because they are just that tiny, we obviously can't use regular, everyday meters to measure them. Instead, atomic radius is measured in nanometers. And to put that into perspective, 1 nanometer is 1 billionth of a meter. That's 10 to the power of -9 meters. Absolutely mind-boggling. Now, since atoms are that small, weighing them is, as you'd expect, pretty tricky. To measure atomic mass, scientists use a relative standard. It's kind of like a fruit seller who doesn't have traditional metal weights. Instead, he takes a watermelon, chops it into exactly 12 equal slices, and then weighs all his other fruit against just one of those slices. Chemists do exactly this, but instead of a watermelon, they use an isotope called carbon-12. One atomic mass unit, written simply as a lowercase u, is exactly 1/12 the mass of one single atom of carbon-12. We also need a way to talk about these elements without writing out their full names every time. So we assign them unique shorthand symbols, approved by an organization called IUPAC.
Some of these are super straightforward, like a capital H for hydrogen, but some have really fascinating backstories. For example, the symbol for iron is Fe because its Latin name is ferrum. Potassium is K, coming from the Latin collium, and copper, that's Cu, which actually comes from Cyprus, the place where it was first discovered.
All right, moving right along to section 4, molecules and ions. Turns out atoms are pretty social creatures. They rarely like to exist all by themselves. Let's explore how they team up.
When atoms bond tightly together, they form a molecule. You can think of a molecule as the absolute smallest unit of a substance that can exist independently, while still showing off all the chemical properties of that specific substance. And these molecules can be made up of the exact same type of atoms or a mix of entirely different ones.
Now, different elements like to cluster in different numbers, and we call this their atomicity. Take argon, for instance. It's perfectly happy flying solo. It's monoatomic. But oxygen almost always travels in pairs, making it a diatomic molecule, which we write as O2. Phosphorus takes it a step further. It clusters in groups of 4, making it tetraatomic. But what happens when metals and nonmetals decide to get together? They form something slightly different, known as an ion. An ion is basically just an atom, or sometimes a group of atoms, that carries an electrical charge. If it carries a positive charge, we call it a cation. If it's rocking a negative charge, it's an anion. And now for the big payoff. Section 5, writing chemical formulae. We're going to take everything we've just learned and use it to write the actual language of chemistry. To write a chemical formula, the very first thing we need to know is an element's valency. Valency is simply the combining capacity of an element. The easiest way to think about it is imagining the number of hands or arms an atom has available to reach out and hold on to other atoms. Let's use a fun analogy to make this crystal clear. Imagine an octopus representing one element, and humans representing another. Our octopus has 8 arms. The humans have 2. The golden rule of chemistry here is that all arms must lock together perfectly. No free hands left just waving around in the breeze. So how many humans do you actually need? Well, one octopus arm grabs one human arm. Since the octopus has 8 arms and each human has 2, that octopus can securely hold exactly 4 humans. If we were to write this as a chemical formula, using O for octopus and H for humans, we get OH4. That little subscript 4 at the end shows us the exact ratio needed to perfectly balance their combining capacities. Let's see how this works using real chemistry and a neat trick called the crisscross method. Take magnesium chloride. Step 1, you write the symbols side by side, Mg and Cl. Step 2, magnesium has a 2+ charge and chlorine has a 1- charge. Step 3, we just crisscross those numbers down to the bottom of the opposite element. So magnesium gets the 1 from chlorine, and chlorine gets the 2 from magnesium. The final result, MgCl2. The positive and negative charges completely balance each other out to make a stable, neutral compound.
Let's try one more, this time with a group of atoms acting together as a single unit, which we call a polyatomic ion. We're going to make calcium hydroxide. Step 1, write Ca and the hydroxide group, which is OH. Step 2, Ca is 2+ and OH is 1-. Step 3, time to crisscross. But wait, because OH is a group of atoms and we need 2 of that entire group to balance out the calcium, we have to use brackets. So we write it out as CaOH2. Those brackets tell us that the little subscript 2 multiplies everything inside.
And just like that, you've learned how to write the language of the universe. We've seen how elements combine to form molecules and compounds, and exactly how to write their secret codes. But hey, remember Dalton's theory from earlier? He said atoms were strictly indivisible. Well, as science progressed, we eventually realized that wasn't entirely true. Which leaves us with one final, pretty provocative question. If atoms are the building blocks of all matter, what on earth are atoms themselves made of? Think on that, and we'll solve that fascinating mystery in our next explainer.